The title of this talk is Security Tokens, Origins, Current Landscape, and Path Ahead. Very exciting. I'm Ron Gearlock. I'm a developer at Tokensoft. Gonna plug my Twitter. It's YouFoundRon. What are we gonna go over today? So I'm going to briefly give some context to tokens on Ethereum by talking about ERC-20. A lot of you, if you're developers, might be familiar with that, so we'll try and go through that fairly quickly. And then we're going to define what an Ethereum-based security token is and why they might be a big deal. And after that, and this is going to be really the meat of the presentation, we're going to take a technical look at some of the implementations with the most traction in the space right now. And then at the end, we're briefly going to discuss the path ahead for security token adoption and further standardization. All right, security token origins. This is the name of the next Marvel movie, by the way. Yeah, and that's the only joke of the night, so buckle in, okay? All right, so what's the technology behind all of this? Who are the characters involved? At a high level, we have issuers. These are, say, a company looking to tokenize their equity. These are people who are minting and deploying tokens. We have exchanges, the marketplaces, where these digital assets are changing hands. And then we have the token holders, and these are the members of the marketplace who actually want to buy and sell these assets. So early on in Ethereum, it became evident that a standard was needed to be able to represent fungible digital assets on top of Ethereum. So ERC-20 is an EIP proposed in 2015 by a developer named Fabian Vogelsteller. I think his GitHub is Frozeman. I don't remember, but it can be easily argued that ERC-20 enabled the ICO explosion of 2017. And this little standard is a pretty simple interface. It's only 6 functions and 2 events. So let's take a look at this interface. The 6 functions start with total supply, balance of, and allowance. These first 3 are what's known in Solidity, which is the language we're looking at, the language of smart contracts on Ethereum, as constant functions, which is to say that they're read-only. When you call a constant function, you're pulling information off of the Ethereum blockchain. So the first one, total supply, it's an accessor for getting the total supply of the token. You might use the return value of this to calculate, say, a market cap. Balance of is another constant function that takes one argument, that is the Ethereum address of a token holder, and it returns their balance. Allowance, and this will make more sense in a bit, this is another constant function. It gets the spendable amount of tokens for an account that a token holder has approved to spend on their behalf. More often than not, that account is a smart contract, and we'll talk about why in a second. So the next 3, these are the actual destructive functions. They update contract storage. The first one, and definitely the most popular, is transfer. And that takes the balance of 2 accounts and changes them to represent the transfer of tokens. Transfer can only be called by the sending account, so the account that already has tokens. And then approve and transfer from kind of, they're somewhat coupled. Approve updates that allowances reference by setting a number of tokens to be transferable by another account, and then transfer from is similar to transfer, but it's callable by that approved account. So you can see the from argument, that would be the account that gave its approval to the spender calling transfer from. And then it also comes with 2 events. Transfer is an event that is emitted on a successful transfer or transfer from call, and approval is an event that is emitted on a successful approval call. So we're going to go through a really simple ERC-20 implementation. So on screen, I have kind of the minimum necessary storage variables that you need to be able to implement it. So the total supply variable up there, that is obviously the total number of tokens that we are saying this contract holds. The balances mapping there tracks token ownership per Ethereum address. So mappings in Solidity are data structures that map a key to a value. The key in this case is an Ethereum address. The value is an integer. Allowances, again, is a mapping, and this one is tracking those spendable token allowances per spender address, per token address. And then in the constructor, we're assigning the full balance to the address that deployed this contract. So message.sender, that will be the Ethereum account or smart contract that deployed this token contract. And this is a common way of minting tokens, you'll see, is just assigning the full balance to the deployer. All right, so now we have those constant functions I mentioned. These implementations are pretty easy. So total supply is just returning that total supply variable that we defined up above. You might wonder, well, like, why even track it? Why not just return the number in here? But if your token contract did something more advanced, like say, allow the owner of the contract to mint more tokens or burn tokens, you might want to actually update that value. So that's why we would return it in here. And then balance of looks up an address in our balances mapping. And one question you might have is, well, what if there isn't a recorded balance for an Ethereum address? Well, in Ethereum, or I should say in Solidity, integer variables default to 0. So if there isn't a balance recorded, it's just going to return 0. And then last, we have our allowance get accessor, which is going to look up an approved spending amount by the token owner's address and then the spender's address. This is relevant in the approve and transfer from functions. All right, so here's transfer. That first line there, that require statement, that is going to ensure that the sender actually has enough tokens to transfer. So you can see we're looking up the balance on the balances mapping, making sure it's greater than or equal to the value that's we're intending to transfer. And then we're updating the appropriate balances. So decrementing the sender's balances amount and incrementing the next token holder's amount. And then emitting a transfer event and returning true. So I think an analogy worth giving is that a token contract is like a really big spreadsheet of account IDs, Ethereum addresses, and account balances, token amounts. And when we transfer tokens, we're just updating 2 rows in that spreadsheet. Another worthwhile thing to note here is that the return type of transfer is a Boolean. So in the actual like ERC-20 spec, it's recommended that you return false if the transfer would fail. But what we've seen the community tending towards is using a require statement and actually reverting the transaction. And the reason for this is because you actually get a failure on chain. And in, say, like building out a wallet or a block explorer, it's a lot easier to see like a failed transaction and say, oh, no tokens were sent, than to see a successful transaction, but then look and see that the return value was false. So kind of a disparity between what the community is doing and what the standard actually says. And like this implementation is actually taken from OpenZeppelin's own standard token implementation. All right, now we have approve and transfer from. So in approve, the sender specifies the spending account and the allowed value, and it emits an approval event, returns true. And then in transfer from, we have 2 checks. We ensure that the token holder has enough tokens to transfer, and then we also ensure that the spender is allowed to transfer the specified number of tokens. So we have to look in that allowed data structure. Again, we emit a transfer event, and that question, why would someone want to let someone else spend their tokens? Well, there's scenarios such as escrow or where scenarios say where Like I have a decentralized exchange and I want that DEX contract to know about transfer of my tokens. Well, when I just call regular transfer, I'm hitting the token contract, the contract that we're implementing. And unless someone is watching that contract and then calling their DEX contract to respond to it, that would be like an oracle, they wouldn't know about that transaction. So if I call approve on the token contract and then call a function on that DEX that now calls transfer from, that DEX contract actually knows about the transfer. So that's why this was needed. All right, so there is some weirdness, and as a result, a couple best practices not outlined in the standard have kind of evolved. First off, there's no floats in Solidity, so how do we track fractional balances? The other thing is deployed contracts only have that Ethereum address to identify them by, so there's not really a human readable distinction that we can make without having to store like an off-chain record of contract addresses and the issuer that issued the contract. So what's emerged is these constant variables, name, symbol, and decimals. So decimals is how we introduce floating point precision to balances. Really the most common value passed is 18 because that's the precision of the Ether token. And then these two strings, name and symbol, that's how we give wallets, exchanges, interface builders a little human readable description and identifier for the token. But it doesn't end here. Another common thing is to prevent transfers to the zero address. So if a sender transfers tokens to the zero address, they have made those tokens unspendable forever. But the total supply recorded on the contract hasn't changed. So if you were doing like market cap calculations based on that total supply value, you would be off. You'd have to go check the zero address and subtract the tokens held there. So many implementations of ERC-20 will add the following requirement to prevent this from happening. And we can call this practice, for the purpose of this talk, transfer restriction. And restricting transfers is the basis for the thinking behind security tokens. What other sorts of scenarios might restricting a transfer make sense? Could these restrictions be leveraged to enable something like, say, on-chain compliance? I think yes. But keeping that in mind, what are the ERC-20 takeaways? We have the ability to represent a fungible digital asset on the Ethereum blockchain. We have a minimal interface, relatively simple to implement, only 6 functions and 2 events. And the standard is already widely adopted by issuers, wallets, exchanges. There are some other, I guess, standards that seek to build on ERC-20 that add things like, so for instance, ERC-777, that adds a couple of extra events for things like burning and minting. And then there's people talking about baking in things that would prevent, say, transfers from the zero to the zero address, or transfers to contracts that can't actually call the token contract. So that's the end of the ERC-20 portion. Hopefully everyone isn't too bored or is up to speed. Now I'm going to talk about security tokens. What's the big idea? So if ERC-20 allows us to represent and transfer digital assets, then I think we can think of the blockchain as this enormous exchange on top of the internet. Why might this be a big deal? Well, if we have a 24/7 exchange, we have potentially this global liquidity pool for these digital assets. And if you're trying to issue an asset, a classic exchange listing is no longer necessary. So if you want securities to enter the hands of public and private investors, you could offer equity as a token on the Ethereum blockchain. But there's a problem, and that is that ERC-20 tokens don't have restrictions on transfers and therefore can be freely traded by anyone. So when you're dealing with securities, this is a big problem. As an issuer, you simply can't afford to allow an unknown person to hold one of your tokens. Essentially, securities are not explicitly fungible assets. And there's laws around how they can and should be able to change hands. What's more, these restrictions depend on how the entity issuing the security is structured and could even change in the future. So we can't expect people to play by the rules, and the issuer is held liable if those rules are broken. But bear with me, I think there's plausibility for security tokens because we could build ERC-20s with extra rules to restrict those unlawful transfers. And we can use the blockchain as a settlement layer with a clear audit trail. And unlike traditional exchanges, because transaction history is now public, we can offset the cost of a lot of compliance measures. And I think with the right approach, we could build out a financial system that is lawful by design and even more efficient. All right, so what's the current landscape? Well, some of the chief concerns regarding the safe sale and exchange of securities are KYC AML. Those are acronyms for Know Your Customer and Anti-Money Laundering. Know Your Customer is actually being able to identify the person that you're giving tokens to. Anti-money laundering is knowing that their financial history isn't criminal. And then in the event that you're distributing a private security, and specifically in the United States, there's investor accreditation. So that's knowing that the token holder is an accredited investor. And then sometimes there's issuer-specific restrictions. So for instance, the SEC or another statutory body could apply limits to like the number of shareholders allowed. I think the current landscape is best represented by 3 implementations of the security token idea we're describing. The first of those is R-Token. This is a smart contract pattern developed by Harbor Network. The second is ST20. This is a smart contract and open standard being actively promoted and developed by Polymath, a security tokens company. And the last one is ERC-1404, a standard being actively developed by Tokensoft. Full disclosure, that's the company I work for. And we make software for token issuers. And we're going to discuss the reasoning around each of these and take a look at reference implementations. All right, so starting with R-Token. R-Token stands for Regulated Token. It was introduced February of this year, and there are several moving parts in the R-Token system. I'm going to read a quote from the R-Token white paper. With the R-Token standard, every transfer occurs if and only if they are approved by a regulator service. So what is a regulator service? In the R-Token system, a regulator service is a smart contract that the R-Token contract, which is a modified ERC-20, calls out to in its transfer and transfer from functions. Between the R-Token and the regulator service sits another contract called the service registry. This contract stores the address of the regulator service contract, and it allows the token owners to replace the regulator service contract address. This makes regulator service contracts upgradable for the token owners. So you could think of the service registry as allowing for like a proxy pattern. And then the last component is a trade controller. And trade controller is just a R-Token specific name for an Ethereum account that has permission to change the regulator service. So from Harbor's white paper, Harbor will be the first trade controller, and the initial implementation of the initial implementation of the R-Token standard. Planned implementations will allow for decentralization of this role. All right, so let's look at some code and diagrams. This is an R-Token contract with a lot of code missing, but what I want you to notice is how that internal check function is used to restrict transfers and, as we will see, emit those check status events. And one interesting aspect of the R-Token spec is that transfer functions never fail on chain. They simply return false and emit a check status event. So this is somewhat of a deviation from how I just mentioned the community at large handles transfers, but it is how this ERC-20 standard defines doing your transfers. But again, people generally favor to revert the function and show failure on chain. This is that internal check function. Here you can see it's being passed all of the details of the transfer, and that internal service thing is the reference to the service registry, which is deployed in the constructor of an R token, and that is getting back the regulator service contract reference, and it's calling check on the regulator service. So the regulator service is being obtained through that service call, and there'll be more on that in a second. But this is the interface for a regulator service. It's just one function, check, and it's being passed all of the transfer details. But presumably, there's a block of code in your implementation that does something meaningful, like check the address against a whitelist, or check whether or not the token is paused, or check if the transfer is to the 0 address, like we saw earlier. So here's what we just looked at, but diagrammed. Every time a transfer is initiated, say Bob wants to transfer a token to Alice, our token calls check on that regulator service. It sends back a reason code, and if unsuccessful, the transfer and transfer functions emit a check status with that reason code. If the reason code is 0, which is reserved for success, the transfer goes through and the check status event is still emitted. Another thing about our token is that there's plans to give the regulator service potentially more authoritative control over transfers through something Harbor calls the mediator. A mediator might be something like a decentralized exchange. So in this scenario, the token holder would call ERC-20's approve method, specifying the mediator as the spender, and a description of the mediator from Harbor's white paper. The approve method can be implemented to include an additional check method. This would mean that the allocation of funds from the token holder to the mediator would require approval from the regulator service. The initial implementation of our token standard will not include this additional check. So something to maybe look forward to from Harbor. This is an implementation of the service registry. The service registry, again, is what's responsible for updating the contract address of the regulator service that the R token contract calls out to. I think one interesting block of code here is the with contract modifier. What that's doing is when the owner is replacing the service, it's making sure, or when the owner is replacing the regulator, the regulator service, it's making sure that the past address is actually attached to a contract, and it does that by using something called inline assembly in Solidity, where it's actually dropping into assembly, and it's seeing that the bytecode associated with that address is actually greater than 0. So there's actually like a contract behind it. So let's look at this role diagrammed. We have an R token. We have the service registry giving that R token the regulator service address. We have our check and reason code exchange. And now we have a regulator service switched out through calling, what was that function called? Through calling replace service, through calling replace service on the service registry. But the interface between our token and regulator service remains the same. It's just check and the reason code. All right, so to wrap up our token, we're going to look at a pretty robust regulator service implementation that Harbor has on their GitHub. We can see up top a bunch of reason codes defined as constants. We have an admin declared that gets defined in the constructor. We have settings and participants mappings created. These are used to store information about counterparties relevant to their eligibility to send and receive tokens. We have a couple of events declared. These are pertaining to administrative interactions with the regulator service. So presumably Harbor is acting as like a transfer agent and updating this regulator service. These are those administrative functions. You can notice that they're designed to handle potentially many tokens interacting with a single regulator service. They all take the token address as an argument. And then this is the important part, the actual check function implementation. So we have relevant checks being made on the transfer arguments with reason codes being returned when restrictions are detected. So this about sums up Harbor's R token. We're going to talk next about ST20. So ST20 was introduced April of this year by Polymath. Polymath is a company that deals specifically with issuing security tokens through their DApp, which is a collection of smart contracts referred to as Polymath Core on their GitHub. Some good stuff Polymath's been doing. ST20 has resulted in an Ethereum improvement proposal that has seen some recent attention called ERC-1400. This EAP was promptly split into two different proposals after being submitted. One is ERC-1410, a partially fungible token standard, and the other is 1411, which is a formalized security token standard that depends on 1410. So we're not going to look at those, but we are going to look at the version of ST20 that sits in their Polymath core infrastructure and has been used on mainnet. So the interface is super simple. It specifies a variable named token details. This is referred to in their docs as an IPFS hash, though the desired format of the file hosted on IPFS is not documented anywhere I could find, but I would presume it's a URI that includes maybe the token's name, symbol, the issuer's website, or their business address. It also specifies a function verify transfer that takes the same arguments as our transfer from function, and it returns a Boolean success value. So maybe you can see where this is going. I think we could think of this as similar to the check function on our token's regulator service. That is a function that checks for transfer restriction logic and determines whether or not the transfer should fail. And then last is a function called mint, which I assume is used to create tokens by minting them to a specific address. Presumably this is how the issuer will do their token distribution. So here's a snippet for an implementation of ST20. This is just the overloaded transfer and transfer from functions. So they're required to call verify transfer and make sure that it returns true before calling the inherited basic ERC20 implementations of transfer and transfer from. And you can see that this differs from our token's approach and falls more in line with the community implementation of ERC20, because if verify transfer returns false, this transaction will revert and fail on chain, and no transfer event will be emitted. All right. Where does ST20 sit in Polymath core? There's a lot going on here, but you can see over to the left that Polymath keeps a registry of tokens deployed on their platform, the Polymath Network Registry, this is called, and the deployment of which issuers pay for in Poly tokens. Poly is a DApp token that Polymath airdropped earlier this year. But this registry, you can see up at the top, also keeps track of a set of contracts that Polymath calls module factories. We're not going to get into too much about these, but just know that they deploy instances of module contracts which can be attached to an ST20 token. Now, these modules are what get referenced in the call to verify transfer and provide our token with its transfer restrictions. Specifically, the transfer manager modules. So ST20 allows multiple transfer manager modules to be attached to it to control the logic of token transfers. For example, a single token could have several whitelists with their own separate criteria for how an address can be added. And you could manage those whitelists in multiple transfer manager module instances. And then permission modules are modules that allow the issuer to give role-based access control to other accounts to manage the whitelist on, say, one of those transfer manager modules. So let's look at the transfer manager interface. I'm going to ignore the inherited general module because it's mainly concerned with how to take fees in Poly tokens. but I want you to notice that Transfer Manager implements verified transfer, but it returns an enum rather than a Boolean. So invalid, NA, valid, or force valid. This is because the validity of the token transfer is based on all of the transfer modules unanimously returning valid, or one of them returning force valid, which is an override reserved for special instances like minting or administrative sending of tokens. And then there's pause functionality on this contract. That pause functionality is for toggling verification checks to the transfer manager. So all of these transfer manager modules can be turned on or off depending on what stage in the token's life cycle it is. So maybe during the sale, there's checks that you want to be doing, but afterwards you want them turned off. And that's actually what's happening in the general transfer manager module. So this is the verified transfer function in the general transfer manager module. And by default, ST20 tokens in Polymath Core get a general transfer module attached in order to determine if transfers should be allowed. And this one behaves differently depending on who is trying to transfer the tokens. So in an offering setting, that would be investors buying tokens from the issuer, the investor's address should be present on an internal whitelist managed by the issuer with the general transfer manager. But in a peer-to-peer transfer, so say after the sale, restrictions apply based on real-life lockups that are enforced on-chain. You can see some of that logic down at the bottom. For example, if a particular holder has a 1-year sale restriction for the token, the transaction will fail until that year passes. So this about sums up ST20. Now we're going to look at ERC-1404. Thank you. So this is currently under active development at Tokensoft. It was introduced September of this year, and we're seeking to simplify and also standardize the handling of transfer restrictions, much like in the previous approaches. So one interesting aspect is that it's not attached to a product or platform. It's not concerned with contract patterns or the issuance process. And as a result, it can be implemented on the token contract itself. However, this leaves most of the decisions up to the issuer, which can be good or bad depending on your mileage. This is the interface. So it builds on ERC-20's interface. It adds just 2 functions. The first is detect transfer restriction, which returns an integer restriction code where 0 is reserved for success. I feel like this is a pattern that is familiar at this point, given RToken's check function and ST20's verified transfer. But what it does differently is have this second function, message for transfer restriction. So given a restriction code, this returns a message string describing the restriction that stopped the transfer. And we'll see why this is a little different in a second. So attempting to bring transfer restrictions down to base principles, here is an ERC-1404 reference implementation. Up at the top, we're defining some restriction codes. 0 is reserved for success. And we also have some messages, and you can see they're like human readable strings. We're putting the actual restriction logic in detect transfer restriction. So we're passing it the transfer arguments. By the way, this is I shouldn't have used this syntax, but in Solidity, if you name your return type, so we see uint8 restriction code, assigning a value to that return type will implicitly return the assigned value. So we're setting it to success code first, and then if the transfer is attempting to be made to the 0 address, we're setting it to the 0 address restriction code. So kind of a tricky syntax if you haven't seen it before. And then in the message in the message for transfer restriction function, we're using similar logic to select the message. We're being passed the restriction code, and you could reasonably imagine using something more efficient like a standardized mapping of integers to messages, talk about that at the end. But yeah, this is implementing an ERC-1404 along the 2 extra functions you're given. And then, similar to ST20, we overload the transfer and transfer from methods. I'm using a modifier here to avoid code duplication, but you can see that we're getting the restriction code by passing the transfer arguments to detect transfer restriction. We're comparing the code with the success code 0, and then this require call is passing the message. This isn't supported yet, but potentially in a new version of the Solidity compiler, you can revert with a message. So this is anticipating that, hopefully. And then if the transfer is restricted, it fails on chain because the predicate passed to the require does not suffice. So it's going to fail. We're not going to have an event log like we did with our token. However, we can still call detect transfer restriction with the parameters that caused it to fail. We can get back the restriction code, and we can actually look up the message. So that's a way that we could fall in line with the community's implementation of ERC-20, but still have meaningful information about our transfer restrictions. So ERC-20, it's sparse. It leaves most of the heavy lifting up to the issuer, but one of the benefits of this is it can sit beneath both our token and ST20, give meaningful error codes and messages to both. I have some examples of this, but I didn't want to put them in the talk, so if you want to see that, you can ask me afterwards, and I can show you these examples. And that brings us to the end, or should I say the path ahead?
The beginning.
Yes. So security tokens are still very novel and relatively unadopted technology. As demonstrated, there are several companies and open source developers working on standards and trying to prime this tech for wider adoption. But what are some of the things that need to happen to move this idea forwards? Well, I think first and foremost is error code standardization. So ERC 1400 and 1411, the EEPs that emerged out of ST20, they're doing a good job of this because they're drawing off of an earlier ERC, ERC 1066, that specifies error codes for, it specifies a pattern for setting error codes, and then in 1411, they have error codes for lockup periods, for an insufficient balance, for sender whitelisting, for receiver whitelisting, for identity restriction, for token restriction, and also token granularity, which is like if you don't want people to be able to send a fraction of a token. And I think that covers most of the basic restriction patterns. The other thing we need is actually like greenlit restriction patterns and more of an established process for these issuers. Like, are these whitelists even sufficient? Does what we're doing on chain even demonstrate compliance? I think this is mostly a waiting game. We're waiting for lawyers and for regulatory bodies to speak up. And then last, if not the most obvious, we need exchange and volume we need exchange volume and we need listings. And this includes decentralized exchanges, but we need to see more market demand for these assets. And I think if we can nail all of these three things, we'll actually see adoption pick up in the space. So thank you. That is probably more than you wanted to know about security tokens. So thank you very much. Awesome.
Cool, so there's questions.
Yes.
Thank you for the presentation. Very clear. Would you like to briefly talk about the difference between utility token and security token?
Okay, so I don't have the authority to tell you the difference between a utility or a security token, but it seems generally utility tokens are seen as tokens that enable an incentive mechanism inside of an application where not having a token wouldn't allow for that incentive mechanism to exist. That's kind of vague, but that's really the best I can explain a utility token. Does anyone have a good example of a utility token? Ethereum. Yeah, Ether. So you need to pay Ether to call any function on a smart contract. And obviously the process around creating Ether makes the resulting transactions immutable and secure, etc.
And for example, EDR, I think the symbol of the token, this is kind of, digital marketing analytics for, mass distribution, not just, big companies.
Yeah, yeah.
And I think the MIT and researchers in Israel are behind this.
Cool. All right.
So what classes of securities like real estate or equity do you think are the best cases like in the near future?
I'll talk about what's most interesting to me, and that is being able to pay dividends on chain. So paying out dividends in Ether by making just like this single contract call. I think that's really cool, and that saves literally thousands of dollars and hours. But that relies on people wanting to be paid in Ether their dividends.
So I have a question.
Yeah.
If utility token is pegged to the Ether, right? Then you can exchange different utilities tokens, right?
So you're saying
If their value is pegged to Ether.
1-to-1? So there's
Not 1-to-1, it can be fraction.
okay, sure.
Yeah, just pegged. Like it's 1/10 of it.
Okay, so then I would think of that token as a unit of account where Ether is like the reserve for it.
So I'm asking whether you can enable exchange of tokens with this characteristic, because it's just a fraction of.
Yeah, you could do that, but you could also exchange a portion of an Ether as well. So it would have to do more than that, I think, to be a utility token.
So at some point you said we are waiting for regulators and lawyers. Aren't you approaching them, kind of actively?
So yeah, the company that I work at, Tokensoft, we try to have as open and frequent discussions as we can with some of these regulatory bodies like the SEC and others, and make sure that we know what they're thinking about it and they know what's happening in the space. So yeah, it takes both working together.
And another question is, what about shielded transactions, like for example Zcash? Do they have anything similar to what you are doing, provided audit trail would not be kind of.
Yeah, I don't know if that would be super appropriate for securities, but that's something really exciting. So over here, or sorry, you're doing mics. Sorry. Yeah.
Is there a best practice between the three organizations that are doing it for reconciling offline or off-chain books with on-chain records?
Are you talking about the issuance process itself? So the actually collecting funds and then distributing the token?
Correct. So someone loses a key. How do you reconcile the offline records with on-chain records?
All right. So yeah. So I think probably the prime idea here is you want to make sure that the Ethereum addresses that these tokens are going to are addresses that belong to people who have passed KYC AML check, potentially also investor accreditation.
And how's that recorded?
So right now, those checks are happening off-chain. There's like no way to do that on a blockchain. And then in the case of companies that provide this, they keep a database of those individuals' contact information and then also the checks that they passed. And then they would, for the issuer, tell them this is the Ethereum address that belongs to this person. You could even go an extra step and have them sign a message with that address, and they'd say, okay, this address is cool to send tokens to, add it to your whitelist. So in all these scenarios, you could manage a whitelist of Ethereum addresses that have been proven to belong to people who have passed those checks. Yeah. Yep.
you get back to the R token check function.
Uh-huh.
What was the regulator service that it calls on?
Yeah, so the regulator service is a contract that it seems like our token would want to, they'd want to either maintain one or many of them and have different regulator services for different, I guess, offering scenarios. And the regulator service is where the restriction logic is checked. So let's say you had a regulator service that holds a list of US accredited investors in a whitelist. And then the people who own that regulator service can update that whitelist. If someone's issuing an R token that needs to only be transferred by US accredited investors, they would point to that regulator service.
Could it check like balance of another cryptocurrency?
Yeah, it could. I mean, it could check for the calling. It could only for the addresses that get passed to it. So it gets the token, it gets the spender, which is more often than not the owner of the Ethereum address, but it could be another smart contract, and then it gets the counterparties, so the receiver and the sender.
Cool. Thanks.
Yeah.
Questions? Well done, Ronald. One more? No?
It's great.
So what actually the regulators say to that? What Securities and Exchange Committee actually?
They're pretty quiet. Ethereum is not a security, though, so we know that at this point.
Yeah, right.
That's about all we know. And maybe. Yeah, so not much so far. It's really the people who are building this out that are, I think, bringing the questions to the litigators. Yeah. Exciting times.
Alex, I feel like you have a question.
Yeah, what's up?
So the question is, do you see interest from, potential customers in the space? And the second one is, so we sort of look at the landscape of Ethereum security token offerings that are enabled by, various smart contracts, right? But sort of, do you think that we need an Ethereum that necessarily? I'm not saying where you need to have you can build a similar thing on EOS or whatever other smart contract platform. That something so simple like Stellar that has minimalistic functionality of a smart contract, which you can build into on top of the core. And have all of the, like, since this is a master node setup, have these things deployed in the banking infrastructure, where all the auditability, right, where you can basically have the read-only functionality for audits. Anybody can sort of audit the transactions. That's sort of the two questions that I have.
Right, so what I think you're asking is, why is everyone focused on Ethereum? Stellar has tokens as like this first class idea. They're not abstracted into contracts. That almost seems better suited. From what I know about Stellar, you can do address whitelisting, which is totally like the most important thing here. But something I don't think you can do is say you just from like an internal governance standpoint said, when we issue equity as a token to prevent like a rogue shareholder taking over and like potential poison pill scenario, we want to limit on-chain the total number of tokens that any account can hold to 20% of the token supply. That is to say, if you tried to send a number of tokens that would cause the balance of the recipient to now exceed 20% of the token supply, that transaction would fail. That you can only do with a Turing-complete smart contract language. That's not something you could do on Stellar right now. So, and those are kind of like really special, specific cases, but they are things that I think issuers might want, and that make, I think, at least for now, Ethereum one of the more attractive platforms. But if you don't need that, then yeah, there's plenty of other chains that you could use to issue.
And then on the other question, the other question is, do you see the demand from potential customers?
I think issuers who are doing this right now are definitely early adopters. There's not some big like flagship tokenized equity company that's super hot that everyone wants to own the tokens of right now. But I think if there is a company, it's really more about the companies, right? If people want to own stock in something, and the only way to own it is by owning a token, then I think that's when we'll see more retail demand for this. Yeah. Or if there's just really great arbitrage opportunities, right? That's another thing too. Yeah. Yeah.
Do you see like the early adopters, like big early adopters? Do you see somebody like Coinbase doing something like this?
I don't know. That'd be cool though.
Questions?
What's your opinion on like the regulatory environment in the U.S. as opposed to places overseas?
It's funny. So before I worked in crypto and I was trying to get into any sale because I knew I could flip it in a couple weeks, and like 3 out of 5 times come out okay. I thought that the U.S. regulations were I felt they were designed to limit non-accredited investors from getting in on potentially really good deals. And now that I'm on this side of the aisle and I see some of the ways that people have not really informed themselves and invested in things recklessly, I wouldn't say I'm on the side of the regulators, but I see both sides now. And yeah, I don't think regulations are ever gonna go away. And I think they're probably a little overbearing right now, but it's okay. It's doing what it needs to do.
Is there anyone, well, let's say, suppose I have some property and I want to write up some legal contract that says this property is now controlled by this contract on Ethereum. Like, can I do that today? I guess like, would then, because it's now a legal contract, then like, would it be enforced, or is it?
I think you would want to involve lawyers. I don't know if you would be required to. It's funny you mentioned that Harbor. They're really targeting real estate investment trusts in particular, or REITs. That seems to be the premier use case that they're advertising using our token for. So, yeah, theoretically, yes. Didn't we learn that someone?
You can't do this today. Yeah, it's possible.
And 2 apartment buildings in New York?
Yeah, there's 2 apartment buildings in New York today.
All right.
Yeah, our clients are doing this with funds.
See, the virus is spreading. It's exploding.
Do you view your token as a complement or a competitor to our token in SK?
What our OUR token, ERC-1404, it's purely like an open source contribution. So I would like to see it used because I know that for people who are implementing wallets, interfaces and exchanges, they could, before even sending a failed transaction, actually do the detect transfer restriction check, get back an error message and show it to the user before they even send a transaction that fails and like waste their gas.
So you're a replacement for our token?
No, it's just a level of standardization that would, I think, give issuers and really the people who are building interfaces around security tokens a better way to build user experiences and a better way to handle these error restriction cases. Yeah.
Thank you very much, Ron. Do we have any last questions? Thank you very much.
Thank you. Thanks a lot.